Suppose we have a finite sample space, S equals A1, A2, up to AN, where AN is some finite integer. And suppose that the probability distribution on S is such that every point, AI, has exactly the same probability 1 over n. N is the number of points in S. In other words, all n outcomes are equally likely or equally probable. In such a case, we can define the probability of a simple event. If A is a subset of S, we'll define the probability of A to be the number of points in A divided by capital N, the number of points in the sample space. This means that for large sample spaces, we'll want to be able to count the number of simple events in a set A without having to list them all. There are two rules that will be helpful in this respect: the addition and the multiplication rule. Suppose we can do a job 1 in P ways, and a second job 2 in Q ways. The addition rule assumes that we'll do either job 1 or job 2, but not both. In this case, we have a total of P plus Q choices, distinct ways in which one or other of these two jobs can be carried out. In other words, the word OR is associated with addition, job 1 or job 2, in P plus Q ways. The multiplication rule assumes that we wish to do both job 1 and job 2. And in this case, there are P times Q distinct ways of carrying this out. The word AND is associated with multiplication. Some useful combinatorial symbols. Suppose I'm interested in the number of permutations of the 26 letters of the English alphabet, taken 10 at a time. There are 26 ways of choosing the first letter in the word, 25 choosing the second, given that we've already removed one, 24, 23, down to 17. This is a special case of a symbol we'll refer to as n to k factors, n superscript bracket k, which is n times n minus 1 down to n minus k plus 1, the number of arrangements of n different elements taken k at a time. You have already met the factorial, n factorial, which is a special case of this with k equals n. N factorial is n times n minus 1 down to 1. The number of permutations of n elements taken all n at a time. Two special cases of this are important. N to n factors is n factorial, but 0 factorial is equal to 1 by definition. N to the power k is, of course, also a product of n factors, all of them equal to n. This is the number of arrangements of n elements taken k at a time where we allow repetitions. Recall, of course, that 0 to the power 0 is equal to 1, and 0 factorial is equal to 1, which means that 0 to 0 factors is, by definition, 1. When k is a non-negative integer, we can write n to k factors as n factorial divided by n minus k factorial. Here are some examples. How many words can you make from the letters in the word Justin if you use all 5 letters? In this case, there are 6 choices for the first letter, 5 for the second, 4 for the third, and so on. Indeed, it's 6 to 5 factors, which turns out to be 720 in this case. Suppose we just use 4 letters. Then the answer is 6 to 4 factors, 6 times 5 times 4 times 3, which is 360. Suppose you use all 6 letters, but you allow repetition. In this case, the answer is 6 to the power 6, or 46,656. You should note that n to k factors is defined whenever k is a non-negative integer. N need not be an integer. Here are a few examples. 3 to 4 factors. This is 3 times 2 times 1 times 0, which is 0. What about e to 3 factors? This would be e times e minus 1 times e minus 2, which numerically is somewhere around 3.35. And minus 6 to 2 factors is minus 6 times minus 7, which is plus 42. Here's a counting example involving 3 dice. I roll 3 fair dice, 1 red, 1 blue, and 1 green. What's a suitable probability model for this experiment? Let A be the event that all 3 dice show different numbers, Find the probability of the event A. First, the sample space consists of triples of numbers like 111, 112, and so on, showing the possible values on the red, blue, and green dice, respectively. Since there are 6 possible numbers on each die, there are a total of 6 cubed such triples in the sample space. This is the number of points in S. The event A is defined as a triple 1, 2, 3, 1, 2, 4, in which the 3 numbers in the triple are all different. There are 6 to 3 factor such points. Essentially, we are selecting and permuting numbers without replacement from the set 1 up to 6. So the probability of the event A is the number of points in A, 6 to 3 factors, divided by the number of points in S, 6 cubed. Here's a second question. Let B be the event that all 3 dice show exactly the same number. Find the probability of B. B consists of triples like 111, 222, up to 666. There are 6 points in B in total, since all 3 dice must show the same number. And so the probability of B is the number of points in B, 6, divided by the total number of points in the sample space, 6 cubed. Let C be the event that at most 1 6 is rolled. Find the probability of the event C. Is determined by evaluating the probability of no 6 at all and the probability that exactly 1 6 is rolled. The probability no 6 is rolled is the probability that all 3 dice show something other than a 6, a value from 1 up to 5. This is 5 cubed over 6 cubed. The probability 1 6 is rolled, well, the 6 can appear in any one of the 3 possible locations. So there are 3 choices of locations for the 6, and then the 2 remaining places have to be filled with a number from 1 up to 5, and this can happen in 5 squared ways. So the probability is 3 times 5 squared divided by 6 cubed. It's either 0 6 or 1 6, or, so we add these 2 probabilities together to get the probability of C. There's another combinatorial symbol that we will frequently use. N choose k, or n to k factors divided by k factorial, is the number of subsets of k elements which can be selected from a set containing n elements. We choose k out of n without replacement. This is the number of ways we can do that. Notice that the order of selection doesn't matter. We're simply counting distinct subsets.